Hello friends, today's question. A particle moves with simple harmonic motion in a straight line in first tau second. After starting from rest, it travels a distance a and in next tau seconds it travels 2a in the same direction then. So we have to find out basically the amplitude as well as the time period of the oscillation. So it states that the particle travels in a straight line with the SHM and it starts from the rest. Okay, so let us first of all write the equation for the SHM. So we have equation of SHM. So it states that if the displacement of the particle is x, which is performing an SHM, then x will be equal to a cos of omega t. So you can say for the displacement x, the particle performing SHM is x is equal to a cos of omega t, where a is the amplitude, where a is amplitude, or we can say maximum displacement from the mean position. Maximum displacement from mean position, and omega is the angular frequency, is angular frequency, and t is the time. So it says that the particle starts from rest, and from there we can say that at t is equal to 0, the particle is at rest at the extreme position. At the extreme position. So from here we can say that the displacement x at time t is equal to 0 will be equal to a. Therefore, we can say from here, thus the particle starts moving from extreme position. So let us now find out the distance traveled in tau seconds, which is given as a, and try to understand what will be the further equations. Motion in first tau seconds. Motion in first tau seconds. So it means our particle, let us suppose this is the mean position, and the particle is at the extreme, so this is the extreme position, and this is our maximum displacement A. So we assume this is our mean position and this is our extreme position, and we say that the distance traveled in, it's given in first tau second, is A. So let us suppose this is the A distance which is traveled in tau seconds. Okay. So therefore we can write the displacement in the first tau second, the displacement in first tau seconds, let us suppose that is given as x1. So we can say our x1 is equal to A cos of omega tau. Let us call this equation 1. And from the figure we can clearly state that this distance or displacement will be equal to A minus small a. So you can see that as the particle travels the distance A, towards the mean position, therefore we can write that our x1, that is displacement from the mean position, therefore the displacement from mean position which equal to x1 will be equal to A minus small a. So therefore we can write from equation 1, we get A minus small a is equal to A cos of omega tau, or from here we can write that cos of omega tau is equal to A minus small a divided by capital A. Let us call this as equation number 2. Now it said that distance traveled in next tau second is 2a. Motion in next tau second. Motion in next tau seconds. Therefore, in the next tau seconds, the particle travels, or because it moves, additional distance of 2a. Additional distance of 2a. So which means that if this is mean position, this is extreme position, and total displacement is our a. In the first tau seconds, we said that it travels a distance, and in the next tau seconds, it travels a distance of 2a. So total distance, once again, this is our mean position, and this is our extreme position. So therefore, the total distance traveled from the mean position will be 3a. Therefore, we can say total distance moved is equal to 3a. So we can write the equation for the, you can say, next tau seconds. Therefore, the displacement in next tau seconds, suppose it is given as x2, so we write x2 is equal to a cos of omega 2 tau. So displacement from the mean position from mean position, it gives us x2 will be equal to a minus 3a. So once again, substituting, let us suppose this is our equation number 3. Okay, so we get from equation 3, we get a minus 3a is equal to a cos of 2 omega tau, and we can find out the cos of 2 omega tau. Cos of 2 omega tau is equal to a minus 3a divided by a. Let us call this equation number 4. So we can solve our cos of 2 omega tau. We can write the formula that we can say, but cos of 2 omega tau is equal to 2 cos square omega tau minus 1 not divided by, but this is our cos of 2 omega tau, and we already know that cos of omega tau we already calculated in equation 1. So we use equation 3 and 4. We use equation 2 and 4. Using equation 2 and 4, we substitute the value, and we get this as a minus 3a divided by a is equal to twice, and this becomes a minus a, and we have divided by a whole square minus 1. Now it is a simple calculation. So we can write this as, this will be equal to twice, opening the square, we get a square plus a square minus 2aa, and divided by a square minus 1. and taking a square LCM, so this becomes a minus 3a divided by a, so this is twice a square plus a square minus 2aa and minus of a square divided by a square. This a and a goes away, and cross multiplying it, we get this as a square minus 3aa, and this is equal to 2a square plus 2a square minus 4aa and minus a square. So this is 2a square and a square, so this cancels out, and we are left with 2a square minus 4aa plus 3a is equal to 0, and this gives us 2a square, and this is minus aa is equal to 0. So taking small a as common, so we get a, and we're left with 2a capital A is equal to 0. So this implies either small a is equal to 0, or we have 2a minus a is equal to 0, but small a is not equal to 0 because we already said that this is a traveling, so this is not possible. This is the only possibility. So we can write here 2a minus a is equal to 0. This gives us that a is equal to 2a. So this is the first part. Now we are going to find out time period of oscillation. Okay. So we can say finding the time period. Finding the time period of oscillation. So from equation 1, we already know from equation 1, we have that cos of omega tau is equal to a minus a upon capital A, and we substitute value of capital A as 2a, so we get here cos of omega tau is equal to 2aa upon 2a, so this comes a upon 2a. Here a and a cancels out, and this is equal to 1 by 2. So our omega tau is equal to cos inverse of 1 by 2, and this is equal to pi by 3. And we also know that but omega is equal to 2 pi by t, because t is the time period. So substituting here, we get 2 pi capital T multiplied by tau is equal to pi by 3, and pi goes away, so we get t is equal to 6 tau. So this is our, you can say, time period of oscillation. Yeah. So we found out that the amplitude of motion, so this is our amplitude of motion, and this is our time period of oscillation of oscillation. So if we check the options available to us, so we can say that the amplitude of motion is equal to 2a. I think there is some problem in the option given to. Okay, so it will be 2a. So let me correct this one. This should be 2a, and here it will be tau, not pi. So option number A is correct, and option number D is the correct option. Because amplitude is either 4, none of the option is correct one. I think I copied the question wrong. So it should be 2a and 6 tau. So this completes the question. Thank you. Here the options were correct. Okay, so option was given as 3a and 4a. Only problem was with 8. It should be 8 tau and 6 tau rather. Okay, so you can say the only option correct is the D. Okay, because 2 is not given option, so you can say the correct option is time period of the oscillation is 6 tau. So this is the only correct option. Okay. So the amplitude of motion is 2a. Neither it is 3a, neither it is 4a. So all these options are wrong. Okay. So only option that is correct is time period of oscillation is 6 tau. So if there would have been an option that is 2a, that would be the correct one. Okay. So I think there was some confusion on my part. Okay. Thank you.